Cool, it looks like we're live.
Yeah, I think so. Okay.
Okay, great. Yes, so welcome everyone to the sixth and final session of the AABI Symposium 2020, where we'll have three exciting talks. First, an invited talk by Jascha Sohl-Dickstein, and then two contributor talks by Matt Hoffman and Alemi. Without much further ado, we'll get to the first talk, which is the invited talk by Jascha Sohl-Dickstein that I'm very much looking forward to. And I don't think Jascha needs a very large introduction, but he's currently a senior staff research scientist at Google Brain, where his research team is interested in the intersection of machine learning, physics, and neuroscience. Previously, he was a visiting scholar at Surya Ganguly's lab at Stanford and an academic resident at the Khan Academy. He earned his PhD in 2012 at Bruno Ohlhausen's lab at the Redwood Center for Theoretical Neuroscience at UC Berkeley. And prior to his PhD, he already had a very stellar career because he was working for NASA, where he worked on the Mars rover exploration or Mars exploration rover mission. And today he will talk to us, unfortunately not about Mars and NASA, but well, I guess fortunately for us, about infinite width Bayesian neural networks. And with that, I'm handing over to you, Jascha, and take it away.
Thank you very much. It's a pleasure to be here. Bear with me for a moment while I switch this back to present my screen. Cool.
Perfect.
Should see the presentation now? Awesome.
Yes.
Yeah, so it is awesome to be here. I promise the stuff I will talk about. I am at least as excited about as I am about Mars. Thank you for the extremely generous introduction. So I'm going to tell you about infinite width Bayesian neural networks. Just very briefly to motivate this, it turns out that as neural networks become wider, they both perform better and often become more analytically tractable. And it turns out that in the limit of infinite width, you can abstract away very often the parameters entirely and make really surprisingly strong closed form statements about the behavior of the network. So I'm going to tell you about some work understanding neural networks and especially Bayesian neural networks in this overparameterized setting. I'm going to talk about a large amount of work done by a large number of people. Just to make sure I give credit, I'd especially like to call out the subset of them listed here, each of whom was a primary contributor for more than one of the results that I'm going to be presenting. Just to read off the names, we have Yasmin, Roman, Jaehoon, Surya, Jeffrey, Sam, myself, Lei Chao, Greg, and George. So why are overparameterized networks an interesting object to study? Basically, they're interesting because they do better. There is a history in machine learning of building larger and larger models and getting higher and higher in accuracy. Even within a given model class, test accuracy tends to increase with increasing model width. Here we show this experimentally in two different scenarios for both fully connected and convolutional architectures applied to CFAR10. Every point on the fully connected plots on the left corresponds to the same architecture and the same depth, but different settings of training and initialization hyperparameters and different widths. In both plots, only models which achieved 100% training accuracy are kept. So the generalization gap here directly corresponds to test accuracy. You can see that if we take the best hyperparameters at each width, then wider models strictly outperform narrow models on test accuracy, out to a width of 20,000, which is as wide as we can go with our compute memory constraints. Similarly, in the right plot, each line corresponds to the same convolutional architecture in terms of both number of layers and nonlinearity used. And for each point on the plot, we are taking the training and initialization hyperparameters that did best on the validation set. You can see that for convnets with pooling as well, accuracy strictly increases with increasing model width. Once again, you see this all the way out to the widest networks that we could practically build. So these observations that we seem to do strictly better with increasing width when working with finite width networks perhaps raises the question, what happens in the limit of infinite width? So in this talk, we're going to examine the infinite or large width behavior of neural networks, and we're going to answer some of that question. We're going to do this both for Bayesian neural networks and for networks trained by gradient descent, though for this audience, we'll focus on the Bayesian networks. We are also going to characterize this large width behavior, both in parameter space and function space. To start with, let's examine the distribution over functions induced by infinitely wide neural networks. Not to spoil the punchline, but we're going to find that infinitely wide neural networks of most common architectures are equivalent to Gaussian processes. I also, before we dive in, want to call out here the link to the neural tangents library that you can see in the middle of this table. This is a neural network library we built. Special credit to Roman Novak, Sam Schoenholz, and Liqiao Zhao, which enables infinitely wide neural networks to be constructed and used as easily as finite width networks can be. I think it's an invaluable tool if you're interested in yourself doing research on infinite width networks. Okay, so let's dive into the Bayesian inference cross function space results. So to see why Bayesian neural networks might be described by a Gaussian process, we're going to start by looking at the distribution over functions induced by randomly initializing a simple, fully connected feed-forward architecture. So just to walk through this architecture has inputs Y0, pre-activations at each layer LZL, and activations after the pointwise nonlinearity phi of YL. The pre-activations are an affine transformation of the preceding activations with weights W and biases B. Both the weights and biases are initialized by draws from a Gaussian with variance sigma squared W divided by width and for the weights and variance sigma squared WB for the biases. The network's outputs or logits at the very top of the network are Z capital L. For simplicity, we're going to assume that the output is 1D. So here, Z capital L is a scalar and N capital L, which is the width of a layer, is equal to 1. We're going to be examining the distribution over network outputs, Z capital L, induced by randomly initializing this network. We're going to derive this for the simple case, but I would like to emphasize that very similar results hold for most common architectures. I'm going to leave this little cheat sheet about the network architecture in the upper right for a while. So before we dive in mathematically, let me illustrate visually what the core result is going to be using a simple cartoon. This plot compares the network's output or logit Z capital L for two different inputs, X and X star. If we were to draw the parameters of the network from their prior and then compute the output of the network for these two inputs for those parameters, that would correspond to 1 point on this plot. If we were then to reinitialize network parameters over and over again and plot the outputs of the network for these two input examples for each of those initializations, then we're going to get a distribution over network outputs, or equivalently a distribution over functions induced by the distribution over parameters. The core result that we're going to get to will be that as the hidden layers of the neural network become infinitely wide, this distribution over functions converges to a Gaussian process. And so the distribution over neural network predictions for any set of data points is jointly Gaussian with a particular compositional covariance kernel that it turns out that we can compute. As a very brief refresher, you can think of a Gaussian process as being just a Gaussian distribution over functions. A Gaussian process is a stochastic process over some continuous domain of random variables, such that any finite collection of those variables is described by a multivariate normal distribution. So, for instance, in our case, the distribution over network outputs for a set of n input examples is going to be jointly Gaussian, with mu providing the mean of that Gaussian and the number of data points by number of data points covariance matrix K, describing the covariance of the Gaussian. You're maybe most used to seeing Gaussian processes plotted as draws of functions over a 1D domain. So for instance, if you look in the lower right, this plot shows several draws from the Gaussian process corresponding to a particular neural network architecture. So you could generate a plot like this, for instance, by where each colored line corresponds to one random initialization of a very wide neural network, and then you're plotting just the input-output map of that very wide network. From this perspective, the plot I showed on the previous slide would correspond to plotting sample values of network outputs, Z capital L, against each other for two different input examples, X and X star. So just want to express that these are just two different ways of visualizing the same distribution over functions and visualizing a distribution of functions which corresponds to a Gaussian process. Okay. Now that I've told you what the result is going to be, let's work through a sketch for why it's true. The loose derivation I'm giving here is closest to that in Roman and Leichau's ICLR 2019 paper, which is the bolded reference. So first, we note that the pre-activations, ZL, are a weighted sum of Gaussian random variables for every layer, where those Gaussian random variables correspond to the weights and biases, and where the coefficients for each of those Gaussian random variables are the preceding activations. So because of this, the ZL are Gaussian, or a Gaussian process conditioned on the preceding activations YL. People sometimes get a little confused about this, so I'd like to emphasize here that the ZL are they're a Gaussian process because the weights and biases are Gaussian. We're not assuming that activations in the previous layer are Gaussian, and we haven't yet taken anything to be infinitely wide. This is true this is exactly true even for finite width. The covariance or kernel of this Gaussian process depends on the second moment matrix KL of the preceding activations YL. That is, KL, x comma x prime, is the covariance between the activation vectors for x, inputs x, and input x prime at layer L. Since KL is the covariance matrix before the affine transformation, you can think of the covariance matrix of the Gaussian process, or the kernel of the Gaussian process, as transforming KL by however it changes due to the affine transformation. Here, the weight scale sigma squared W just changes the overall magnitude of the covariance matrix, because larger weights will just serve to scale up the entries in Y, while the bias is shared for all inputs X. And so the bias tends to make data points look more and more similar and makes the covariance matrix more like a constant matrix. So we just showed that ZL given YL is a Gaussian process. We can observe from the formula that ZL only depends on YL through its second moment matrix KL. Because of this, we can just as readily say that ZL is a Gaussian process conditioned on the second moment matrix KL rather than conditioned on YL. Just for reference, you can see that I've added the equation for the second moment matrix on the right. And so CL given KL is described by the same GP. Okay, this is probably the slide with peak complexity in the talk, and I promise it's not so bad, but also it all gets better from here on out. So the first observation is that K0 is just the data point by data point second moment matrix at the input layer. And then KL for L greater than 0 is just the second moment matrix of YL at layer L, which is computed by averaging over units I in the layer L. But YL is the activations after applying the nonlinearity phi. So we can substitute phi of ZL minus 1 into the equation for the second moment matrix KL. So we can just write YL in terms of the preceding pre-activations. From step 2, we know that ZL minus 1 is a Gaussian process conditioned on KL minus 1. This means that KL is just an average over NL units, each of which is drawn from a Gaussian process. As NL goes to infinity, so as the layer width goes to infinity for intermediate layers, a concentration of measure result applies, and we can replace this average over units with an expectation over the distribution generating unit values. The value of this expectation is deterministic though. This means that in a limit of infinite width, the second moment matrix KL at layer L is a deterministic function of the second moment matrix KL minus 1 at layer L minus 1. We're going to write the deterministic functional that transforms KL minus 1 into KL as F. So we can say that KL is equal to F of KL minus 1. For many common architectures and nonlinearities, we can compute F analytically. For instance, we can do it analytically for ReLU networks or for error function nonlinearities. Even when we don't know how to compute F analytically, it turns out that in most scenarios, it only requires solving a 2D integral. And 2D integrals can typically be computed numerically. For instance, we have code that does this in the neural tangents library. Okay, so that was the hardest step, which is just showing that the covariance matrix at layer L becomes a deterministic function of the covariance matrix at layer L minus 1. Finally, we can just put these pieces together. The top layer logits are described by a Gaussian process given the second moment matrix K capital L of their preceding Y capital L. In turn, each of the second moment matrices are deterministic functions of the second moment matrix from the layer below. So by applying this recursively, you can find that the top layer logits are a Gaussian process conditioned on the second moment matrix of the inputs and thus conditioned on the inputs. This GP has a particular compositional kernel, which can be found by applying F to the input kernel L times, which we're going to write as F capital L here, and then accounting for the variance sigma squared W of the readout weights and sigma squared B of the readout biases. So the distribution over functions computed by a neural network after random initialization is described by a Gaussian process with a particular compositional kernel, which we know how to compute. So that's pretty cool. So now that we have a closed form analytic expression for the distribution over functions computed by a randomly initialized wide neural network, what can we do with this new understanding? So first, we can observe that network initialization just corresponds to the very beginning of neural network training. So if we can understand the properties of the neural network at initialization, it should allow us to make strong predictions about whether the network will be trainable. Second, this result actually holds more generally for Bayesian neural networks. As we'll discuss, for Bayesian neural networks, this equivalence doesn't just apply to the network at initialization, but also holds for posterior predictions on test points. So let's start with predicting trainability. In order to evaluate the trainability of the network at initialization, we can look at what happens to the second moment matrix KL as the network becomes very deep. The evolution of the second moment matrix, the number of data points by number of data points, covariance matrix K with depth, is a recurrent process. With every layer of the network, we apply F to K over and over and over again. One common behavior of recurrent processes is that if you run them long enough, they will converge to a fixed point. And generically, that they tend to decay towards this fixed point exponentially. That is also what turns out to happen here. So we can write KL, K capital L, in terms of a fixed point K star plus a term which decays exponentially with depth over a characteristic depth scale chi c. In order to understand trainability, we can look at how this decay towards a fixed point changes as a function of the initialization hyperparameter sigma squared W for the weight initialization and sigma squared B for the bias initialization. Here we illustrate this for a network with tanh nonlinearities. When sigma squared B is large, the shared bias vector causes dissimilar inputs to converge with greater depth. And the fixed point corresponds to activation vectors for all inputs becoming identical with constant covariance matrix entries. On the right side, on the other hand, the tendency of large weights to push apart initially similar inputs dominates. And no matter how similar inputs start out, they become increasingly dissimilar with depth, as captured by the scaled identity contribution to the covariance matrix. These two behaviors induce ordered and chaotic regimes, where all inputs either become identical with depth in the ordered regime, or where initially similar inputs become pushed apart and the network essentially acts as a hash function in the chaotic regime. This talk has so far focused on forward propagation of activations and on the distribution over network logits being a Gaussian process. A really cool observation, though, is that gradients are linear operators, and a linear transformation is still a linear transformation of a Gaussian is still a Gaussian. And subject to some weak constraints, this also is true of a Gaussian process. So if a function is described by a Gaussian process, then its derivative is also described by a Gaussian process. This means we can do a nearly identical analysis of the input-output Jacobian of the network as we did for the forward propagated activations. When we do this, we find that in the ordered phase, the Jacobian norm goes to 0 and gradients therefore vanish. In the chaotic phase, because small changes to the input cause large changes in outputs, the Jacobian norm goes to infinity and gradients explode. As you might imagine, both of these behaviors make training deep neural networks extremely difficult. There's a line down the middle, though, where something different must happen. Along this critical line, the two tendencies perfectly balance. K does not, the covariance matrix K does not exponentially decay towards a fixed point, and the gradient does not exponentially explode or vanish. It seems perhaps plausible that in order to train an extremely deep network, this line, this critical line, would likely be the good place to do it. So in fact, we find that to be true. Here, I'm showing an experiment where we train a vanilla convolutional neural network with no residual connections or batch norm or any of the other usual tricks or techniques that are used in very deep networks. We do this with an initialization, which was carefully chosen to lie on the critical line. We also chose the initialization to satisfy another property known as dynamical isometry, which demands that the Jacobian spectrum be well conditioned, but I'm not going to dive into that subtlety here. By doing this, by initializing on the critical line, we were able to train convolutional neural networks up to depths of at least 10,000 layers with near identical train and test curves as we had for shallower networks. This is orders of magnitude deeper that have been achieved with vanilla convolutional architectures before this work. So cool. By looking at the distribution of functions at initialization, we are able to gain insight into the hyperparameters at which neural networks will be trainable. And in fact, that insight seems to directly enable us to train networks that we would have otherwise been unable to train. I've just shared results for analysis for fully connected and convolutional networks. But similar approaches can be applied, as I mentioned earlier, to analyze most common architectural components. I'm not going to go through all of these listed down the left, but let me briefly tell you about one or two results where this style of analysis supplied surprising insights. So here I'm showing an analysis of the effect of dropout on trainability. Each pixel in this image corresponds to a network of a specific depth L, initialized with a specific weight scale sigma squared W, and the bias scale sigma squared B is fixed for this entire plot. The color of the pixel corresponds to the achieved training accuracy, where redder corresponds to higher training accuracy, and this is training for some fixed number of steps. The dashed line is a multiple of the characteristic depth scale chi-c, and indicates our prediction for the maximum trainable depth. Surprisingly, in the presence of dropout, you can see that there is no critical line, and the maximum trainable depth is always finite. Qualitatively, you can imagine that what happens in the presence of dropout is that dropout erases a fixed fraction of the information about the input with every layer, such that information about the input decays exponentially towards zero with depth, making training impossible. This is likely suggestive for why dropout works great for shallow networks or on side chains in ResNets, but does not work, for instance, on the recurrent path in RNNs or in other situations where you try to apply many layers in a row with dropout. This is also, by the way, likely a qualitative behavior that would be seen for most other approaches to noise regularization. I was going to additionally show you some experiments around batch norm, but I think in the interest of time, I won't. I'll just tell you a brief, perhaps surprising takeaway from batch norm, which is that you find that for any choice of hyperparameters, the batch norm operation induces a chaotic input-output map and exploding gradients, just always. So if you have a very deep network with batch norm at every layer, then at initialization, your network is effectively a hash map, and this falls out of the GP/light phase diagram style analyses that I just showed for a couple of networks. Cool. So we've just shown that the equivalence between wide networks and GPs allows us to both predict trainability and also to gain insight into the properties of deep networks. Now, let's talk about how the same equivalence allows us to perform inference with infinitely wide Bayesian neural networks without ever even instantiating a neural network. So first, let's look at Bayesian posterior estimation using the same cartoon I used earlier. So here, let's imagine that X star is a test point and X is a training point. And we know that the network output should be 1 at point X. That is our training data set. Like output equals 1 for input X is our training data set. This is equivalent to slicing this joint distribution over train and test outputs along this blue Z equals 1 line, so along the training label. However, because we have 2 equivalent ways of writing this joint distribution, which is either like drawing parameters randomly from the prior orphan over and over again, or writing down the analytic form for the GP. We also have 2 equivalent ways of writing any conditional or marginal or posterior distribution, which is derived from this joint. For instance, one way in which we can make fully Bayesian predictions is to draw parameters from the posterior distribution over parameters given the training data, and then evaluate Z capital L for the test point for each of those parameter values. So here in this updated plot, the x-axis is the logic value for the test point, and the y-axis is the probability of observing that logic value. And the distribution over test set predictions from this posterior parameter method corresponds to black delta functions. The other way in which we could evaluate the Bayesian posterior is just to compute in closed form the posterior distribution under the corresponding Gaussian process. This is indicated in red. In the infinite width limit, these 2 approaches will converge to exactly the same distribution over test predictions because they converge to exactly the same joint distribution over train and test model outputs. That is, we're interested in the Bayesian posterior over test points. And we could either compute this by sampling parameters from their posterior and then evaluating the corresponding test prediction for each of those parameter samples, or we could compute this by directly evaluating the distribution over test set predictions as defined by the GP in closed forms. And those 2 ways of evaluating it are equivalent. This means that if we want to evaluate the predictions of a wide Bayesian neural network, we never have to instantiate a network at all, but can just evaluate the corresponding neural network Gaussian process instead. We just to call out the paper in the lower right, George derives this correspondence of the function space posterior and the parameter space posterior much more formally in the reference shown there. We will also, in a few slides, show some empirical experiments using this correspondence. But before we do that, let's zoom back out to the high-level picture for a moment. So we just discussed how infinite width Bayesian neural networks correspond to Gaussian processes and how this provides insights into the behavior of different architectures and makes it possible to predict when they will be trainable. It turns out that in the large width limit, neural networks trained by gradient descent also become like really surprisingly simple objects. Specifically, sufficiently wide neural networks behave as linear models around their initialization throughout gradient descent training. In parameter space, this means that the model can be replaced by its first order Taylor approximation, while in function space, this means the predictions of the model become the same as those from a kernel machine. I'm only going to discuss the infinite width limit of gradient descent trained networks at a really high level, but let's just try to build some intuition for it. The core effect is that in the large width limit, the infinite number of units in intermediate layers of the neural network each change by an infinitesimal amount over the entire course of training. Similarly, the infinite number of parameters throughout the entire network each individually change only infinitesimally. The net effect of an infinite number of units changing infinitesimally throughout the network is that all those infinitesimal changes sum up to produce an order 1 change in the network output, which is how learning occurs. However, because each of the units and receptive fields in the middle of the network change only infinitesimally, they can all be replaced by their first order Taylor approximation. So in the limit of infinite width, it turns out that throughout training, a neural network can be replaced by its linearization. That is, the output of the neural network will correspond to its output at initialization plus its parameter gradient at initialization times the change in parameters, and then plus a term that goes to 0 with increasing width. I'd like to emphasize that this does not mean that wide neural networks become linear networks. Their output is still a super complicated nonlinear function of their inputs. It's just that throughout training, the change in their outputs is linear in the change in their parameters. This does mean, though, that wide neural networks become equivalent to a random feature model, where those random features correspond to the gradients of the network output with respect to the parameters. And training involves learning the coefficients for each of those random features. I should also call out that the neural tangent kernel paper develops these same ideas, but working exclusively in function space rather than parameter space. So we tested this empirically by comparing the logic values for test and train output and the train and test loss and accuracy for a wide ResNet architecture compared to the linearization of that same architecture. We find surprisingly good experimental agreement between wide neural networks and their linearization until quite late in training, when we perform training with a small learning rate. We do find, though, that the linearized model deviates and falls behind the nonlinear model late in training and behaves very differently when trained with a large learning rate. There are many techniques in deep learning that break the correspondence of wide networks to linearized networks. For instance, large learning rates and auto-regularization, and these are areas that are being actively explored. You should maybe check out our recent catapult dynamics paper if you're interested in one type of deviation of real networks from linear networks. I also strongly recommend Greg Yang's recent paper on feature learning in infinite networks for better understanding these deviations. More than just predicting how a single network will evolve through training, for MSE loss, we can actually solve for how the full distribution over functions induced by like random initializations of neural networks evolves throughout training. From the first part of the talk, we know that the distribution over functions at init is a Gaussian process. We also know how a Gaussian distribution evolves under linear dynamics. The distribution over functions that result from gradient descent training of wide neural networks with an MSE loss then turns out to be a Gaussian process throughout training. I should emphasize, though, that this does not mean that gradient descent is Bayesian. The GP that you get from gradient descent training of randomly initialized wide neural networks is different than the GP that you get for wide Bayesian neural networks. And the GP from gradient descent trained networks does not correspond to the posterior distribution of any well-formed prior. To emphasize the sometimes really surprisingly good performance of these NNGP and neural tangent kernel methods, let me briefly share some results from a reverse ablation study we performed. So here, we started out with a base configuration for finite width networks, where we expect them to be very well described by theory. We started with finite width neural networks trained with a very small learning rate, with no regularization and with no early stopping, and for relatively large widths. We looked at this for 3 different architectures: fully connected networks, CNNs with a linear readout on their top layer, and CNNs with global average pooling. All experiments were on CFAR10. We then compared the accuracy achieved by this base case network to the accuracy achieved by the corresponding infinite width Bayesian and gradient descent trained networks, or the NNGP and NTK kernel-based networks. We find that for fully connected architectures and CNNs without pooling, the infinite width neural networks do consistently better than the base configuration of finite width networks. For CNNs with average pooling on the other side, on the other hand, the infinite width network does better. For both finite and infinite width networks, though, performance can be dramatically improved above this base case by a variety of interventions. And most of these interventions break the correspondence between infinite and finite width networks. So for instance, training with a large learning rate, or data augmentation, or L2 regularization, or early stopping, all dramatically improve the performance of finite width networks, as you can see in the rightmost column in the finite network pane. I think it will be super interesting to see how far we can push the infinite width network equivalent kernel methods as we develop analogous interventions and techniques that improve their performance. As part of that same study, we also compared the performance of infinitely wide Bayesian neural networks against that of infinitely wide networks trained by gradient descent. And we found that infinitely wide Bayesian networks typically, although not always, achieve better test performance than infinitely wide gradient descent trained networks. So here in this row of plots, for each data set and architecture, we are plotting the NNGP and NTK test accuracies against each other for a variety of input preprocessing techniques. Points above the diagonal line correspond to NNG predictions being higher than NTK predictions, and points below the diagonal line correspond to the NTK performing better. You can see that most points are above the diagonal line. This observation then is that infinite width Bayesian networks do better than infinite width gradient descent trained networks, which might be perhaps somewhat satisfying news for many of you. Returning to our high-level table, so zooming back out to our high-level table, we've now filled in 3 of the boxes, but you may notice a suggestive gap. One way maybe to choose research projects is to fill in suggestive gaps like this one. In that spirit, I'm going to share an extremely brief, and even briefer, because I think I'm just about out of time, sneak preview of some early work using results from large width limits of neural networks to efficiently draw posterior samples in parameter space from large networks with many parameters. So I'm just going to motivate this with a few observations, and then I'm going to show you a pretty but super preliminary plot. So maybe the observations are that, first of all, drawing posterior samples from Bayesian neural networks with current technology is extremely hard. It's so hard that it's almost never even attempted in practice. Most work building Bayesian posterior approximations for deep networks use some type of variational approximation. The second observation is that if instead of a super complicated deep neural network, we had a linear or affine model, then generating posterior samples would be extremely easy. In fact, we could do it in closed form. This would just be Bayesian linear regression. The third observation is that, as we've just discussed, sufficiently wide neural networks behave a lot like affine models. So this makes you wonder, is there any way we can use this correspondence of wide networks to affine models to efficiently sample? And the super short answer is yes. I am not even going to go into this at the depth that I was going to on this slide. I'm just going to say that we use the near equivalence of wide neural networks to linear models to propose MCMC transitions, which would exactly sample from the posterior if wide neural networks actually were affine models, and then we're able to correct for the deviations from wide neural networks being exactly affine using standard Metropolis-Hastings reduction. The plot on the right is a super simple sanity check demonstration that this technique works. In black, we show 3 training examples that we are going to fit with a Bayesian neural network in just 1D. And here in blue, we are plotting the distribution over posterior functions we generate by sampling the parameters of a roughly 2 million parameter 4-layer Bayesian neural network from their posterior. And you can see that it agrees very closely with the analytic posterior we get from the NNGP and differs from the NTK analytic distribution over functions that would result from gradient descent training of an infinitely wide neural network. So, in summary, I have presented what I believe to be a powerful framework for theoretically analyzing neural networks. It can be applied to either Bayesian or gradient descent training of a neural network in either function space or parameter space. I've further shown that this perspective enables to predict how trainability depends on architecture and hyperparameters. It also allows us to do semi-magical things like compute test set predictions that would come from inference with infinitely wide neural network without ever even instantiating a neural network. It's also provided several insights into network behavior, for instance, showing that noise regularization limits trainable depth, that batch norm induces chaos in deep networks. I didn't talk about this, but it's highlighted some connections between the role of equivariance and weight sharing in CNNs. Finally, I showed some promising but very preliminary results where we're able to use this large width limit to enable better posterior sampling of parameters for infinite width Bayesian neural networks. Also, as I mentioned at the start of the talk, we have an open source library for constructing both finite and infinite width networks. Link in the center. If you're interested in reproducing some of our experiments or running experiments of your own, you should check it out. All right, thank you very much, and sorry for taking so much time.
Thank you very much. That was an amazing talk with very exciting results, and I think also a great overview of what happened in the last couple of years, driven both by your lab and by other labs as well. Thank you very much. So we have already 2 questions, and I'd ask the audience if you have any questions, then just please add them to the Q&A. And so the first question is by Mark, and it regards the analysis of the gradients that you talked about in the beginning. So taking gradients of a Gaussian process is again a Gaussian process. And Mark's question toward that point is that that backpropagation usually is concerned with gradients with respect to the parameters, whereas the derivatives that you were talking about, so taking a derivative of a GP still being a GP, is with respect to the inputs, if you understood correctly. And the question is how these two gradients and analyses relate to each other. Yeah.
Okay. So that is an excellent question, and Marcus is completely right. The answer maybe is that the gradient with respect to the parameters looks like an outer product of the backprop signal which you get from the Jacobian and the forward activations. So you have like activation times like delta vector is your gradient update. And so what the Jacobian tells you is it tells you how large the contribution from the backprop signal will be. It doesn't tell you how large the contribution from the forward prop signal would be. And for tanh, the forward prop signal is always going to be roughly order 1, because like tanh is like a bounded nonlinearity. But for other nonlinearities like ReLU, where the forward propagated signal can like diverge to positive infinity or 0, then you also need to worry about the scale of that term.
Great. Thanks. I hope that answers Mark's question. And the second question is by Alexander. I'm just going to read it out. Could you elaborate? Isn't it possible to describe the behavior of infinite width gradient descent trained nets through the NTK? And to some extent, one should be able to derive the change in the Gaussian process distribution from the initial neural network GP through time with the NTK and how it changes the NTK GP distribution. And so his question is, how are these intuitions, how does this relate kind of to the intuition that you talked about, and how and why are they different?
Like how is the NMGP and the NTK different? I guess the NMGP, if you're thinking about gradient descent training, then the NMGP just describes the distribution of functions that you get at initialization, whereas the NTK describes the distribution over functions that you get for after training the neural network. You can write down the equation for the distribution over functions that you get after training a neural network for like time t. And if you set t equals to 0, then you get the NMGP. And if you set t equals to infinity, then you get an expectation something driven by the NTK. And for t between those two, you get some mixture of the two. But it is definitely true that the neural tangent kernel describes the evolution in function space of neural networks with gradient descent training.
And how does that relate to the update that you described, where you do the kind of infinitesimal update to each parameter individually? Because those at instantiation are basically an NMGP, and I guess once you train those, do they then turn into an NTK?
Yeah, awesome. Okay. I think I better understand the question. So you're maybe asking, what is the connection between the linearization and the neural tangent kernel? And the answer is that they are exactly the same thing. Just one is in parameter space and one is in function space. And maybe one way of seeing this is any kernel method you could cast as being a random feature method. So like there's an equivalence between a kernel and like learning like linear weights to a set of random features. And so you can imagine that equivalence is the equivalence between like the neural tangent kernel and the linearization. And then maybe another piece of this, I'm not sure if this is the question or not, but let me just say it, is that linearization holds for a single random initialization of the parameters. So you randomly initialize your neural network, and then throughout training, it looks like an affine function. And if you did a different random initialization of your neural network, you would get a different affine function. And so linearization, at least the equation that you see on the screen right now, is just to do with a single initialization. I think often when we look in function space, we look at the full distribution over functions, which would correspond to many random initializations.
Yeah, that makes sense. I hope we answered the question. I think he still wrote something in the chat, but I'm not entirely sure. But I think we're also out of time, so I think I would leave it at that. And then if there's any other questions, I'm sure you don't mind if Alex reaches out to you directly.
Oh yeah, please.
Yeah, so with that, I'd like to thank our speaker, Jascha, again, and then move on to the first contributor talk, which is a talk by Matt Hoffman on roundoff errors in Metropolis Hastings accept reject steps. And the way we'll do this is that Darwin will show the YouTube video that was for this contributor talk, and Matt will be made a panelist and can then answer questions in a written Q&A afterwards. So you can ask questions during the talk while we show the video, and then Matt will answer both in writing, but then we'll also have a short Q&A via video as well. I hope that made sense.
Thank you again.
Thanks.
Am I sharing the slides now? I guess
Yes, you are.
There was some apparently network disturbance again, but let's hope it works fine. Okay, let's start.
My name is Matt Hoffman. I'm going to be talking to you today about roundoff error and its effects in Metropolis Hastings accept reject steps. So, if you take nothing else away from this presentation, the thing you should take away is that if you're not careful, Metropolis Hastings might reject a lot if you use low precision arithmetic, especially if you have a lot of data. So to illustrate this, on the left, this is the acceptance probability of a Hamiltonian Monte Carlo Metropolis Hastings algorithm on some synthetic linear regression problems with different amounts of data as a function of iteration number. And you can see the acceptance probability is essentially 1 if we do it in float 64. If we drop down to float 32, the situation becomes much worse, especially as the size of the data set increases. So I'll spend the rest of the time trying to give you some intuitions for why this happens and what we can do about it. Metropolis Hastings is really a meta-algorithm. It takes a target distribution, P of theta. This could be like P of theta given X if we're trying to do Bayesian inference. Right, so the way the algorithm proceeds is each step we sample a proposal theta prime from Q of theta prime given theta and accept it with this probability alpha, which is the minimum of 1 because it has to be a problem. Right, so this accept reject step ensures that the stationary distribution of this procedure is in fact P of theta, and so this gives us a way of actually generating samples from the distribution we're interested in if we do it long enough. So there's this very significant trend in machine learning towards using ever lower precision arithmetic, right? And there's some advantages to this. It reduces your memory requirements. It lets you get quite a few more floating point operations per transistor. In this talk, I'll focus on good old single precision float 32, but in these lower precision formats like float 16, B float 16, tensor float 32, all these things are becoming popular. And they do seem to work surprisingly well if you're doing stochastic gradient descent on deep neural networks. So, you know, fine. But, you know, Metropolis Hastings does, at least in principle, assume that we're doing exact arithmetic. So to what extent does it matter that we're not really using real numbers? So I'm going to talk to get at that question. First, I'm going to talk a little bit about what I mean by roundoff error. So there's one type which I'll call simple truncation. I'm not going to spend a lot of time on it, but basically this is just a question of how many significant figures are there in a 32-bit float. The answer is about 6. So this means that we can't even really represent very large log densities. So here's a little example of a way in which that might be a problem. But I think the bigger issue is accumulations of catastrophic cancellations. So if we're doing Bayesian inference, often we're interested in this log joint P of theta and X, which up to a constant is the same as log P of theta given X. And often that's a sum of many terms, right? A log prior plus a sum of log density, log likelihoods for each of these xn's. Now, naively, summing these terms leads to each time we do an addition, there is a little roundoff error, and those many little roundoff errors wind up getting added together, and they can actually accumulate into much bigger roundoff errors. And this seems to be a much bigger problem than simple truncation. So, for example, if we try computing 2 million Poisson log likelihoods for a variety of random different rate parameters in float32, then if we do everything in float32, then we get the error distribution on the left. Looks vaguely Gaussian. It's got a magnitude of around 1. Whereas if we do the sums in float64 and then just truncate, then we get this much smaller amount of error that is much more well-behaved. So now let's talk about roundoff in Metropolis-Hastings algorithms. So just a little terminology first. So we'll call the inaccurate rounded off log density that we wind up computing log p hat of theta, which is just the true density log p of theta plus an error epsilon of theta minus a log normalizer that makes it so that p hat is actually a distribution that's properly normalized. But it'll cancel out everywhere we look at it. Right, so this leads to this perturbed Metropolis-Hastings acceptance probability, which is actually the acceptance probability that we wind up computing and plugging into our Metropolis-Hastings algorithm. Right, it winds up just being, we plug this p hat into the standard Metropolis-Hastings ratio. So that means that if we're doing Metropolis-Hastings with limited precision, essentially what we're doing is actually sampling from, or rather at least we're leaving this perturbed distribution p hat invariant. So how is p hat different from p, the thing we actually want to sample from? Well, the first thing we might worry about is bias, right? So p hat, the way in which it's different, right, is it assigns higher probability to states with larger round-off errors, epsilon. Now, we might worry that expectations under p hat might be different from expectations under p, but they'll probably be pretty similar, and this is a pretty hand-wavy statement, but they'll probably be pretty similar to the expectations under p if, first, h, the function whose expectation we're interested in, is relatively smooth, and second, this error function, this round-off error function, epsilon of theta, doesn't have a lot of low-frequency components, right? So basically, if it's fluctuating around some constant value, basically because round-off error is driven by low-order bits, which should be fluctuating fairly quickly, as long as it's fluctuating kind of fast enough, then it probably shouldn't change our estimates of h too much. But that's maybe not an easy assumption to verify. But I would say that as big an issue is, does the algorithm even do an okay job of sampling from p hat, right? So there's this issue, right, that p hat assigns arbitrarily higher probability to states with larger round-off errors, but we don't have a way of preferentially proposing those states. We have to wait until we get lucky and get a large positive error. So intuitively, if epsilon has heavy tails or high variance, then basically once we sample a really big epsilon, we're stuck. We have to keep sampling until we get, just purely at random, another similarly extremely large round-off error. And so, for example, if the round-off error is normal under p hat, then that means that the error epsilon is log normally distributed, and that means that our acceptance rate, e to the epsilon is log normal, and that means that our acceptance rate goes down exponentially fast in the variance, and there's a derivation of that in the paper. So here's an empirical example coming back to that HMC on linear regression in a little bit more detail. So here, this is just a bunch of different synthetic data sets of different sizes. Step size chosen very conservatively so that the acceptance rate is extremely high in float64. And as we might expect, in float32, the round-off error does increase pretty much linearly with the number of examples because we're just adding more and more terms to that log density. And the acceptance rate does go down roughly as predicted by the derivation for the normal case in the paper as the variance of the round-off error goes up. Now, the purple and red dots are a little bit higher, the acceptance rates, than what's predicted, but I actually think that's just because we haven't actually converged to p hat yet, because the acceptance rates are so low that our mixing is terrible. So, what do we do? Well, first, how do we know that this is happening? Some warning signs that I've run into. One is just signs of round-off in the log density, right? So if you have these massive magnitude log densities, like minus 48 million, Clearly, you just don't have enough significant digits to the right of the decimal place to expect good things to happen. Another issue, another warning sign is that the acceptance rate doesn't go to 1 even if you decrease the step size, right? So a corollary is that if you do step size adaptation, trying to target some acceptance rate, those adaptation algorithms usually assume that if you drive the step size to 0, then your acceptance rate will go to 1. And if that assumption is violated, then the step size adaptation algorithm is just going to keep struggling to drive the step size low enough to get good acceptance rates. It never will, and so you'll wind up with a step size of 0. Finally, of course, the smoking gun is that if you can do things in float 64 and you see that they yield significantly higher acceptance rates, that's obviously very compelling evidence. So how do we solve this problem? Well, of course, one option is to do everything in float 64, but that might not be palatable. For example, if you're running on a consumer-grade GPU. Another option is to compute all of the terms that are going into that big sum in float 32, but cast them to float 64 before summing so that you get rid of those catastrophic cancellations. Similarly, you can also stay in float 32, but use a compensated sum technique like consummation. Another little trick is that you can write these log ratios as a sum of differences rather than a difference of sums, right? So you have a bunch of these y's whose log density you're computing. Take the difference between their likelihood under the proposal and the original state before you do the sum rather than after. And that actually makes those things zero mean and can help a lot. And then finally, hardware permitting, stochastic rounding could potentially be a solution in some cases. So in summary, roundoff error can ruin a perfectly good Metropolis Hastings algorithm. It is possible to get float 32 to work, but you do have to be careful. On the flip side, I would say that the big advantage of float 64 in this case is not so much that you have to do it, but it does make your life a little bit easier if you can afford it. Finally, watch out for these warning signs: big log densities, low acceptance rates, and this step size adaptation death spiral. Thanks a lot.
Cool, thank you very much. So if the audience has any questions, then feel free to either write them in the chat or in the Q&A. And I think while you do that, let me just get started with 1 or 2 questions. So I guess one, I was very much caught out by this when I first watched the talk and read the paper. And I was wondering, there's this field of probabilistic numerics that tries to analyze computation from a stochastic perspective, and you could take all of these things into account. And I was just wondering, I guess this is a more meta question already, how this might relate, and what lessons one can take from there that might be useful for this community.
Yeah, that's a good question. I'll admit that I'm really not an expert in this. I guess despite having claimed to have written something that somebody should read, but I until very recently was blissfully ignorant of a lot of this stuff. So someone else may actually be better able to answer this question than I. I guess I would say that the paper and the talk really discuss kind of what happens within the Metropolis Hastings correction, and I think that so I think they're under kind of pretty simple error models. The situation does get pretty bleak as the variance of the error gets large, or the scale of the error gets large. That said, there are algorithms such as Langevin or Hamiltonian Monte Carlo that, or Gibbs for that matter, that if you're conservative in the right way, then you can get rid of the Metropolis Hastings correction. And in some cases that might be fine, right? And I think that's an interesting, I think there's been quite a lot of analysis of Langevin in the presence of gradient error, and what happens to Langevin when you omit the Metropolis Hastings correction. It would be interesting, I think, to see if it was possible to take some of the lessons from the probabilistic numerics world and use those to analyze what happens in Langevin and HMC when you have these errors that are not, the usual kind of mini batch sampling errors or discretization errors that we usually think about.
Yeah. Okay. Thanks a lot. And so some questions have come in now. So Alex Alemi asks, if float 32 already looks kind of bad, what does this tell us about even lower precisions like B float 16?
Yeah, I mean, it doesn't look great, right? I guess I would say, if you want to do, and again, this is all assuming that you want to do the Metropolis Hastings correction, right? It may well be that in some cases you can get perfectly reasonable performance using these lower quality or these lower precision formats. But I mean, even when you're doing SGD, right? Sometimes we do see that B float 16, sometimes it works fine and there's no problem at all, and sometimes it is really, and sometimes it really hurts you, And I think if you want to kind of play it that close to the edge of what the hardware of what the numerics will tolerate, then I think you've got to be willing to sort of pay a little bit of a price for that in the form of checking whether that's really a problem. I mean, like I sort of alluded to it in the last slide there, I think one of the things that I realized in the course of thinking about this stuff is something that, of course, like people who do classical kind of numerical simulation stuff have always known, which is that the real advantage to higher precision formats isn't necessarily that there are things you can only do in those higher precision formats. It's that the cost in human time of implementation testing time of getting your algorithms to work with lower precision formats may outweigh the benefits in terms of the amount of compute that you get access to from dropping down in precision, right? Because that's always a constant factor at best.
Yeah, that makes sense. And then let me just see. There were a couple of other questions, but I think we're slowly running out of time. So I would suggest that maybe you answer the questions in writing while we move on to the next talk. Perfect.
Excellent. Thanks, everyone.
Then, thank you very much. We come to the last talk, which is a contributor talk by Alex Alemi. And I think Darwin was having some technical issues with sharing the screen because his internet connection wasn't very reliable, unfortunately. So Alex, would you be able to share your screen and show the video from your end? Or if you want, I guess also give the talk live if you prefer that, if you're sharing anyway.
I think I could give it a shot. I'm
sorry that we're putting you on the spot right now.
Yeah, that's all right. Let me just second. This one.
Yeah, sorry, my internet normal.
Yeah, so is this showing up now? Is this fair or?
Yeah, that's showing up.
Okay, so I guess I'll play the video then. Oh, this is actually the wrong one. Sorry.
You can also, I mean, if you want to, you can also give the talk with the slides, although I'm putting you very much on the spot there.
Yeah, I think I'll try to see if I can get the oh no, the actual thing. Just a second. Sorry. This one I think is it. Here we go. All right, I think we're good to go.
I don't think it's playing, but there's no sound with the video, unfortunately.
There's no sound in the video.
But that might be because I think when you share, you have to share and say share computer audio as well.
Oh, new share. This one. Okay, well, I'm going to abandon ship and I'm going to instead, I guess, try to give the talk live. So you have to bear with me for 1 second while I didn't see the thing to share the audio as well. So you know what? We're just going to do it live. See what happens here.
Thank you very much for that. And very sorry that that we're putting you on the spot there.
That's all right. Hopefully it's decent. So, okay, so now I'll try to share this again. Okay, so hopefully this is showing up.
Yes.
We're good audio-wise and screen-wise?
Yeah, both working fine.
Excellent. So, okay, so, oops, how do I? All right, so here going to present a paper we submitted VIB as half Bayes. And sort of overall, the point was just sort of an observation that we made where you can think about the variational information bottleneck method, which it doesn't matter if you're not familiar with it, don't worry, we'll kind of talk about it, but really we're trying to explore a sort of half Bayesian approach. Is there some way that we can kind of get some of the benefits that you get from Bayesian inference, giving yourself some sort of generalization guarantees without the sort of full machinery? So that's kind of what we sort of investigated here. And so I think it's best illustrated by means of an example. So here, imagine you have a very simple setup where we've got data distribution. We're going to have it be uniform in X from -5 to 5, and we'll have the Y, the targets, be normal from like a cubic with some noise. So here, plotted in orange is the true distribution of the data. Now, if we were to draw some data from it, right, here are like 10 samples from that joint distribution. Here would be some, 10 other samples. Here would be, I think, 100 samples. And we want to fit a model to this. We want to try and capture the true joint distribution. So for that, we need a model. And why don't we, everything's neural network these days. We'll do that. Let's take a feed-forward neural network with 32 hidden units, and we'll use it to parameterize a predictive distribution. So here we'll take our like 2-layer feed-forward neural network. That'll be like, Z is f of x and theta. It has parameters. You give it an x position, and now it gives you some like representation z. And then we can use that representation in order to parameterize our predictive distribution. In this case, we'll take it to be a normal. We'll use the sort of 0th component of the output. It'll be a 2-dimensional representation as being the mean. And we'll send the, the second component of this 2-dimensional representation through like a softmax function in order to get some representation of the standard deviation. So if you do this, you spin the thing up, you randomly initialize the network. This is what it looks like. Now blue is the predictive distribution, showing the sort of 1 sigma bounds. And what we really want would be to try to minimize the sort of true risk, right? So if you think about what we've done here, you imagine now, if we really had access to everything, what we would want to do is to ensure that we get our model as close as possible to the true joint distribution. So in the space of all possible distributions over parameters for our network, in expectation over all possible draws over X, we would look at the expected value of the output of the network, and we'd use that to parameterize our predictive distribution. We take expectations with respect to everything, and we'd compute, the KL divergence, or if you want, just maximum likelihood if you drop the constant with respect to the true, we want to maximize the likelihood under our model under these conditions. And if you do this in this case, like if you actually give yourself access to sort of an infinite amount of data, an infinite number of draws from this joint distribution, and you just do gradient descent for, several 100,000 steps, it completely nails it, right? This problem is like the model can do it perfectly, and you end up with sort of perfect agreement between the model's predictive distribution and the true distribution. You can see in the corners measured by KL, it's very small, right? 12 millibits basically. But we don't often have access to an infinite amount of data, so we only have a finite amount of data. In order to deal with that, we usually just kind of like fly by the seat of our pants, and instead of optimizing this intractable objective involving the expectations with respect to the joint distribution, we take empirical averages with respect to the samples that we saw. And so, if we return to our example, let's say we only have 10 data points, we randomly initialize our network, and now we just maximize likelihood with respect to the 10 samples that we see, sort of taking averages rather than the expectations. The model sort of completely nails this task, right, in the sense that it does a fantastic job of maximizing the likelihood on those 10 points. But in so doing, it massively overfits, right? Our predictive distribution in this case completely sort of collapses. It ends up putting sort of 0 uncertainty on each of those 10 points. The model like perfectly interpolates through the data, and as a result, the actual KL divergence between our resulting predictive distribution and the true distribution is massive, thousands of bits. It really does sort of a terrible job. Of course, if we increase the amount of points, like here we go from 10 points to, I forget whether this was 100 or 1,000 points, eventually the model, is only so expressive, and it starts to sort of not be able to interpolate the points exactly. And, you know, as a result, it actually starts to get better agreement. I mean, this isn't fantastic, but it dropped from 1,000 bits to 300 bits. You know, if we took infinite data here, this is probably 1,000 points. We can actually get good agreement. Like once we sort of overwhelm the capacity of our predictive model, things start to work out. And this is just, you know, I guess a more direct way of, you know, given enough points, it looks like it's an infinite number of points eventually. But I'll remind you, you know, yeah, infinite number of points, things work fantastically. So how do we get around this in practice, right? How do we avoid overfitting? Well, you know, that's what we're all here for, right? Bayesian inference offers us some kind of guarantees. And to like ridiculously oversimplify things, one way like that I've come to appreciate that you can sell Bayesian inference is that it provides certain guarantees provided by sort of a, you know, these pack bounds. So at the heart of it, what are they doing? You would like to minimize some true risk with respect to some distribution. And if by invoking things like the compression lemma and stuff, you can actually stochastically upper bound an expectation of a true risk in terms of the expectation with respect to the empirical risk, as long as you add a sort of KL divergence term. The way I like to think about this is, you know, by kind of specifying a KL divergence with respect to some kind of quote unquote prior, something you specify before you look at the data, it keeps you honest, right? If you keep one foot inside the door, it's hard to get overrun by the truck. So you can provide certain guarantees that you won't overfit by ensuring that you don't veer too far from a thing that was sort of guaranteed not to overfit, namely some prior that you specify before looking at the data. But as a sort of mechanism, what pack bounds let you do is take a thing of this form, right, a true loss, and upper bound it by an empirical loss, as long as you kind of are willing to add the appropriate KL term. So seeing what happens if we return to our true risk, the thing that we decided was really a good idea, and I guess I didn't emphasize, but I'm using blue here to denote true expectations and reds to denote empirical. If we look at the form of this true risk, the way that I wrote it, which is kind of funny, you can identify everything in this orange box as being, you know, a true loss. And then if we kind of turn the crank of pack, we can turn everything in yellow into a version in purple, and we can replace this whole thing with now an expectation over parameters of a empirical risk plus a KL term, now a KL in terms of the same distribution that we took the expectation with it to. And even though this also might look like a way you're not used to seeing it, this is sort of a way to specify what a Bayesian neural network would be, sort of more or less exactly. If you minimize this objective, if you look in the space of all possible parameter distributions for the parameter distribution that minimizes this objective, that is another way to specify the Bayesian posterior distribution. And, you know, so now we see like one way to think about it is it's guaranteeing that you don't overfit by utilizing a pack bound. In this particular case, we can go back to only having 10 data points. And if we minimize this loss precisely, we end up, you know, we do the Bayesian neural network thing. We actually end up with a decent fit. I mean, this thing, the KL divergence between the resulting predicted distribution and the true distribution is quite small, you know, 0.2 bits in this case. But, you know, it took a lot of work. This was doing HMC and all that stuff. So what if there was some way to kind of do some middle ground? And I guess that's the kind of point here is going back yeah, what does that mean? So in most problems like this regression case, there's actually, you know, there's a joint distribution. There's two random variables at play. There's the X's and then there's the Y's. So hypothetically, imagine if we return to our original problem and we still only have 10 X positions that we're going to query this function at. But let's say at each one of those X positions, we could actually generate or draw like an infinite number of Y values. So an infinite number of, you know, targets at each of those X query points. And we could take that, you know, this half empirical sort of target. Like what if we, you know, we're only going to take 10 empirical X points, but we're actually going to take a loss with respect to expectations with respect to the targets. If we did that in this neural network case and we minimize that using like an infinite number of draws, we end up with this. And this is pretty good. I mean, this model on the 10 points that we're sort of adding a constraint in this loss, it does a fantastic job of matching the true distribution. And because it's a neural network and neural networks sort of interpolate reasonably well, between those 10 data points, it's doing something reasonable and smooth and nice, so that the resulting KL divergence, the resulting predictive KL, is also quite small, 0.27 bits. And this still only ever seeing 10 X positions that we query at, but using just multiple Y samples. So again, this thing is intractable. We can't actually take true expectations with respect to targets, but can we kind of turn the Bayesian crank, but only for half of the objective? So if we return to our funny way of writing the true risk, it involved two expectations, an expectation with respect to the x's and an expectation with respect to the targets. What if we kind of draw a yellow box just around that second part and try to protect ourselves from overfitting to a finite number of target samples? By running the pack crank, you take the thing in orange, yellow, you send it through the bound, you get out this thing in purple, and you end up turning that true expectation into an empirical expectation plus a KL term. Now a KL term involving the thing that you're taking an expectation with respect to, which in this case are the outputs, the sort of distribution of outputs of the neural network before we sent them into the predictive function. And yeah, that's sort of the idea. Turns out this objective is also kind of precisely a way to write the variational information bottleneck objective, which was a previous paper of ours. And in the context of this simple example, it actually can do something sort of interesting. So now if you search in this possible parameter values for the parameter values that would minimize this objective, one that involves empirical target samples, but a KL term looking at the outputs of the sort of neural network, you can end up with something that sort of does reasonably well. The model, even though it has the capacity to, doesn't shrink its predictive uncertainty to zero. It doesn't concentrate too closely on those 10 data points. It sort of knows that it shouldn't trust the precise placement of the Ys directly, and sort of smooths them out and does a reasonably job of kind of interpolating between everything else. And you end up with a decent KL divergence over the whole sort of predictive domain. And this is with basically no computational overheads associated with just ordinary neural network training, because all of the sort of expectations, everything is happening in a lower dimensional space. This isn't doing inference in the space of a few million parameters of the neural network. It's just looking at a distribution of activations, in this case, two-dimensional activations at the top of the neural network. You can control the tightness of the bound, just like an ordinary pack or an ordinary Bayes, by adjusting the sort of temperature. Here, the effect of that temperature has the effect of changing the degree of confidence the network has in the targets. And yeah, that's really kind of bring to the end, just this kind of like thought experiment. What if we could try to be half Bayesian? What would that look like? And an identification that one way of trying to be Bayesian is something we've talked about before. But to kind of summarize, Bayesian neural networks, in order to get your generalization guarantees, you consider a distribution over all possible parameters of the network, several million usually. In sort of the variational information bottleneck, you're really only talking about activations over the final, or distributions over the final activation, which is usually a much lower dimensional space. Bayesian neural networks can sort of guarantee you or offer you certain generalization guarantees having to do with finite joints. Variational information bottleneck, in so much as it provides anything, it's only talking about the target samples, not anything having to do with the, where you're sampling the function, but what the targets are. Bayesian neural networks arguably are costly and difficult, whereas variational information bottleneck is sort of cheap and easy. So it also seems to work. Some of our other works, we've done things like this and show that it can improve robustness, it can improve generalization in large-scale image classification things. And yeah, so to summarize, the real thought experiment is, for a lot of problems out there, I think instead of requiring full generality, full generalization guarantee with respect to finite number of samples from the joint distribution, there's lots of problems for which, if only you could have multiple target samples for a fixed number of input samples, you could hope to kind of do noticeably better. And there might be much cheaper ways to achieve that than sort of fully Bayesian neural networks. So I think that's the end. I actually don't see anyone, so I guess I'm going to, I have no idea what that was in terms of time or anything. I'm sorry for the...
No, you were perfect. You were perfect. I would have interrupted you if you were running over time.
Okay.
No worries.
Excellent.
Thanks for doing this on the spot. And I'll ask the audience again to submit questions. And the first question that came in is in the chat. I'm not sure if you can read it yourself. It's probably easier than if I read it out, because I realized earlier that reading out questions is harder than actually you reading it and then maybe asking a question so that we have it in audio and then answering it.
So I guess I'm not sure if I'm seeing which question we're referring to.
In the chat, hang on, let me just read it out.
Oh, from Matt, I guess.
From Matt, exactly, yeah.
So IIUC, this argues that VIB is most useful when there's significant aleatoric uncertainty. So I'll admit the Greek words always confuse me, but I think I'm going to agree, right? So precisely, one of them is data uncertainty, the other one's model uncertainty. Whichever one of those is the one that would benefit from, or, yes, for problems in which I think there is non-trivial, what I would call data uncertainty, meaning like there is stochasticity in the observations that is not reducible. I think those problems, right, are subject to a kind of overfitting that other problems aren't. And I'm saying that this sort of half Bayesian slash what VIB I think is trying to do is protect against that kind of overfitting, or in so much as it can guarantee anything. It can help you sleep at night in that you might not overfit to that kind of overfit in that way.
Yeah. Maybe a related question that's a bit heretical in the Bayesian workshop, but I guess there's a lot of frequentist methods that try to kind of scale your uncertainties after you've trained your model on some empirical distribution. So either by using quantiles, or I mean, there are these temperature scaling methods as well. What do you think of those compared to such a half Bayesian approach?
Yeah, so I mean, in practice, a lot of those techniques work, but I do think that a lot of them, I guess, like I feel like a lot of the empirical methods and temperature rescaling and things like that, they do sort of rely on the fact that our models they are limited in their predictive capacity, especially, right? They rely on the network not being able to make too confident predictions on the training set, and then you can kind of walk back the confidence of the predictions. But
I guess if it overfits completely, if the mean function is completely off, then it's very hard to recover from that. And I guess that you're more protected from that, I guess.
Yeah, I think, it seems like what the objective is trying to accomplish is, precisely sort of not taking the observed targets too seriously and preventing that collapse from sort of ever happening. Yeah.
And maybe as a last question, what type of applications or larger scale experiments did you look at? Because you showed these very simple 1D plots, and I think they're very good to gain intuition of what's going on. But then I guess the question is also always how they translate to larger scale problems.
Yeah, so I guess in the 4-page workshop submission, we didn't do very large scale experiments, but this is so. I guess the point was more of the story, identifying an alternative derivation of where this style of objective might have come from. But we have, me and my colleagues have been sort of looking at VIB for lots of other applications. I think, completely biased opinion, but the places where we seem to see the most benefit are in what you might call like robustness style things. So out of distribution detection, we saw some results there, and perhaps the strongest, largest scale empirical results are that CEB paper I flashed up, but on like ImageNet classification and CFAR, we achieve nice robustness to like ImageNet C and adversarial examples, like the sort of traditional robustness measures on these large scale image classification data sets. That's the sort of like largest scale studies we've done.
Yeah. Cool. That sounds very exciting. Thank you very much. I think there are no other questions. And then with that, I would like to thank all our 3 speakers again for a very interesting session. And apologize for slightly running over time and having some technical issues there. And I think with that, we're also closing the entire symposium. And thank you. Thank all the speakers. Thank all of you for attending. I hope you found it as interesting as we did. And we'll be sending out a brief questionnaire shortly, because there will be probably another AABI symposium that will have to be virtually by the end of this year or next year, and the beginning of next year. And we want to take any learnings that we can on how to improve the format for the virtual world. Thank you very much, and goodbye, everyone.
Thank you.